All right, so this is limits to infinity, and these are applications of those limits. So let's try one. A big box store determines the cost in dollars of creating a competing Star Wars toothbrush called Space Wars toothbrush. Is this cost function, where x is the number of toothbrushes? So c is our cost, and x is the number of toothbrushes. First thing we're going to do is find the average cost. So average cost for that number of units is just the cost to make that number of units divided by the number of units made. It's average cost. If you want to find out the average of something, you add up all of the costs and you divide it by the number of toothbrushes you've made. So if we plug this in, like that, and then we divide it by x, we end up with a rational function. So this only has one term on the bottom, so we're going to just divide it. All over x. So there is our cost function, our average cost function. Oops, I have an extra 0 in there. So 4, 5, 4, 5. I keep wanting to put a 0 there, make them cheaper. 250. 576 over x. All right, so now we have our average cost. So if you were to plug in 10, it would tell you the average cost to make 10 toothbrushes, but they're going to be making millions. So really, if you plug in 1,000,000, it would tell you the average cost for 1,000,000. So let's take a look at this function real quick for 1,000,000 toothbrushes. So we plug in our function, and I've already changed my window to, it'll include 1,000,000 now, and I hit zoom 0 to get the graph. And there you can see our average cost is decreasing, which makes sense because as you make more toothbrushes, it's going to cost you less to make each toothbrush. So if I hit trace and I plug in 6 zeros, make sure I'm right, 1, 2, 3, 4, 5, and I hit enter, it says my average cost is 70 cents. So 1,000,000 toothbrushes would cost me 70 cents a toothbrush. That's what it means. All right? So what we want to know now is what is the limit of the average cost as x approaches infinity. Now, it's not going to actually approach infinity, but we're in that direction. So if we plug our average cost in there, 4, 5 plus 250, 576 over x, we already know that the limit as x approaches, let me write that in red, our main rule, the limit as x approaches infinity of 1 over x to the r is equal to 0 with r greater than 0. So definitely we have a 1 here for our exponent, so that's going off to 0. And so what are you left with? 0.45, and this is dollars. So it's going to be 45 cents a toothbrush. So what does that mean? Well, if you think about it, this is our cost to manufacture each toothbrush. And what this represents is the startup costs. Well, with these big box stores, they're going to be making millions and millions and millions of toothbrushes and sending them all over the world. So these startup costs will eventually just start to disappear as this goes off to infinity. So the average cost is 45 cents per toothbrush. And that's what it costs them to make them. And so as it goes to infinity, this just becomes pennies of a penny. It's a percent of a penny, and it gets smaller and smaller and smaller and smaller. So they can have really large startup costs to manufacture stuff and still not charge very much for it because they're making millions. This is why they can put out little small stores and little small things. You got to make sure quality is over their quantity. All right. Population of a community is given by this function, where t is in years. What can you expect the population to be in the long run? So let's look at our limit. So in the long run, all they're saying is as x approaches infinity, that's what we want to look at. Long run, x approaches infinity. And in this case, it's not x, it's t. So if we take our function, 40 over t squared plus 10 minus 50 t plus 1 and plus 70. Well, we already know that this is an application. So if you sit there mathematically, we can divide every single one of these by the denominator, which is t squared. So we would end up with the limit as t approaches infinity of 40t over t squared, and then t squared over t squared minus 10 over t squared. And then we do the same thing with the 50. The bottom is a t. So t over t minus 1 over t, and then plus 70. You don't have to do anything with that one. And again, we always pick the bottom so that we end up with a number that is not 0 on the denominator. So this equals the limit as t approaches infinity of 40 over t, 1 minus 10 over t squared minus 50 over t, and then 1 minus 1 over t plus 70. And so now we can just say, oh, you go to 0, you go to 0, you go to 0, and you go to 0. And so what do we end up with? We're going to end up with 0 over 1, which is 0. And then 0 over 1, which is also 0, plus 70, which is just 70. Well, what does P represent? The population, so people. So we're seeing that this town is decreasing to 70 people. So that's it. It's going to eventually become 70 people. It's a prediction, approximation. That's it. All right. Last one is my favorite. Let's read it. The function blank gives the body concentration in parts per million of a certain dosage of medication after time t in hours. Find the body concentration in the long run. So basically as t approaches infinity. So what you're thinking about here is you take some sort of medication in. How long will it stay in the body? That's what we're looking at. So forever means our t is approaching infinity. So if we plug that function in here, and then we divide everything again by t, so that's the biggest one on the bottom, we get limit as t approaches infinity, 0.8t over t plus 1,000 over t, so on. Let's simplify. All right, now we can say u go to 0 and u go to 0, and we're left with 0.8 over 5. And if we plug that in our calculator, we end up with 0.16. And it's parts per million. So how much is left in the body? 0.16 parts per million. So it's still left there. It didn't fully disappear. That's what this formula is saying, is that if you take this medication, it will be with you for life. All right, and there's what you use our limits to infinity for. Thank you.